Welcome to the next lecture on modulation techniques for mobile communications. The brief outline for today's talk is as follows. We will first summarize what we have learnt in the previous classes. Then we will look at constant envelope modulation techniques. We will look at binary frequency shift keying or BFSK, followed by minimum shift keying, and then something which is used in modern GSM systems, Gaussian minimum shift keying or GMSK. Finally, we will have a small glimpse at Emery PSK. So, this is the outline for today's talk. First, a brief recap. Last time we learnt the linear digital modulation techniques and why they are better than analog modulation techniques. In particular, we talked about binary PSK or phase shift keying. Then we learnt that you can use differential phase shift keying in order to do the same thing without the use of the carrier. You don't have to get the phase information to use DPSK. We then moved on to quadrature PSK or QPSK, one of the very popular modulation techniques. Then there were problems with QPSK because of the switching, and there were possible switchings of 180 degrees in the symbols, and hence we proposed another technique called offset QPSK, which only allows a maximum of 90-degree phase shift between symbols. And then a compromise between QPSK and offset QPSK called the pi/4 QPSK, wherein we use not one but two signal constellations of QPSK shifted mutually by pi/4, and you use alternately each one of the constellation diagrams. Now, today we are going to focus on constant envelope modulation techniques. What are the advantages of constant envelope modulation techniques? First and the foremost is power efficient class C amplifiers can be used without introducing degradation in the spectrum. Please remember, the basic requirements of any modulation technique is A, the spectral efficiency, B, the power efficiency, and C, how easy or difficult it is to design the receiver. Here you can have very cheap power efficient class C amplifiers that can be made use of for constant envelope modulation. The other important feature of constant envelope modulation techniques is low out of band radiation of the order of as low as -60 to -70 dB. So, really low out of band emissions, which is very good because my receiver low pass filters and band pass filters do not have to be very strict. Then all this leads to simplified receiver design and high immunity against random FM noise and signal fluctuations due to Rayleigh fading. So, in general, the constant envelope modulation techniques fare much better in the Rayleigh fading environments, and hence a favorite choice of many wireless communication systems. First, let us start with binary frequency shift keying or BFSK. Clearly, we have one bit per symbol, and we denote frequency 1 or FL lower frequency to send symbol 1, which is representative of say 0, and frequency FC plus delta F for bit 1. So, 0 is denoted by this symbol on the left and 1 is denoted by the symbol on the right. If you plot it, a lower frequency represents 0 and a higher frequency represents 1. So, what is the modulator doing? Modulator is just a multiplexer where you have a select bit in, and it chooses between S0 and S1, lower frequency and higher frequency depending upon whether the bit is 0 or 1, and sends it. Clearly, there is a problem. The problem is the moment you switch, the transitions may be abrupt, and any time I have abrupt transition, abrupt phase changes, I will have out of band emissions, spurious emissions. This is bad news. So, suppose we take an example for binary FSK, and the data sequence that I am trying to send is 1011001. So, 1 is depicted by a higher frequency, 0 is depicted by a lower frequency, high frequency, low, low, high, and so on and so forth. But the moment the symbol interval, which is also the bit interval in this case, gets over, you shift to the next symbol. But at the time of transition, you have phase discontinuities. Question?
Sir, is there any fixed ratio between the higher frequency and low frequency?
Yeah, question being asked is, can there be any fixed ratio between the higher frequency and lower frequency? The answer is yes. Actually, we need the higher frequency and lower frequency to be orthogonal in some sense. That is, integrated over one symbol interval, the integration should yield 0 if I integrate V1t, V2t. So, there will be some possible spacing, and as you have higher and higher spacing, you can reach a number of solutions. The minimum shift possible, which will still render it orthogonal, will lead us to a minimum shift keying situation. But here, in a very simplistic scenario, we are showing that we have two symbols, one denoted by a lower frequency and one denoted by a higher frequency. Also, we can put in another constraint as to the phase continuity part, which we will talk about in the subsequent slides today. The point to be noted from this slide is that phase discontinuities will occur if we use a simplistic binary FSK modulator as shown in the previous slide, and this is not acceptable. This is called discontinuous FSK. So, we have to work around this. This is clearly not an acceptable solution. The answer comes in the form of continuous phase FSK, or also called CP FSK. Here the solution is simpler. We have a constraint on the number of cycles that we have, and the continuity at the transition is maintained. So, there must be a relationship between the number of cycles here and the number of cycles here. Clearly, if you see, the lower frequency has 2 complete cycles and the higher frequency has 1, 2, 3 and 4. This is logical. So, if frequency f1 is twice of f0, we meet this constraint. Even if we have the frequency f1 4 times f0, again the constraint will be met, and so on and so forth. So, you can have as much separation between f1 and f0 as possible, but you are clearly interested in the minimum possible separation, because we do not want to be very expensive in terms of the bandwidth requirement. What we understand from this slide is, for the same data stream as discussed previously, I can have an FSK which is continuous phase. So, no phase discontinuities at symbol boundaries, hence continuous phase frequency shift key. Now, let us see what are the problems associated with phase discontinuities. Phase discontinuities pose several problems like spectral spreading and spurious transmission. Both are highly undesirable, especially in a regulated environment. So, we need a continuous phase FSK, something similar to analog FM, except the modulating signal is a binary waveform. So, if you remember from one of your previous lectures, you have an FM which has the frequency proportional to the input signal. Here, instead of having a continuously varying message signal, we have a binary waveform consisting of ones and minus ones, and we modulate the FM using that. So, this will ensure that I do not have phase discontinuities. So, my signal S subscript f of FSK T can be represented as under root 2 EB over TB. EB is energy per bit, TB represents the bit duration. Cosine 2 pi FCT, this is my base frequency, plus this is the modulating signal, and M eta can be binary +1 or -1. This will yield a continuous phase FSK. Please note, even though M eta can be discontinuous, the integration minus infinity to T M eta d eta multiplied by 2 pi f k is not discontinuous. This whole thing will be a continuous phase signal. Now, how do we build a transmitter? A very simplistic transmitter is as follows. We have two modulators, cos 2 pi f1t and cos 2 pi f2t, pertaining to 0 and 1, and we have a binary data sequence coming in, and we have an on-off level encoder, and then here we pass it through an inverter which will multiply it to cosine with f2 as a frequency. The other part is f1, add it up and send it out. So, it is a clear implementation of the formula for binary FSK. What about the detection part? So, it is both possible to have a coherent detection and non-coherent detection of binary FSK. First, let us talk about the coherent detection part. So, the coherent detector is just the inverse. Logically, the received signal is divided into two parts. The first part is multiplied with cosine 2 pi FCT, and second one from sine 2 pi FCT, integrate, add, pass it through a decision circuit and get an output. Why are we multiplying this? Look at the FSK waveform, and we have this 2 pi FCT being split here, multiplied, integrated, and a decision circuit has been passed through. Let us talk about the non-coherent detection. This is the block diagram for non-coherent detection of binary FSK. Here on the left is the FSK input. Again, you split it into two parts, but this time we have logically a band pass filter at lower frequency and a matched band pass filter at higher frequency. F subscript L stands for the lower frequency part and F subscript H stands for the higher frequency part. Clearly, we have two frequencies, one of the frequencies representing 0, the higher frequency representing 1. Once you pass it through an envelope detector. So, there is no need to know the carrier. This is non-coherent detection. Add it up, pass it through a decision circuit. So, please note that the two symbols 1 and 0 pertain to the cos 2 pi FLT and cos 2 pi FHT pertaining to the lower frequency and the higher frequency terms. Now, how does the FSK spectrum look like? Please remember, this is also an important part in choosing a modulation technique. How does the spectrum look like? Where are the main lobes ending? How high are the side lobes? What are the locations of the nulls? These are the questions that have to be addressed before we choose any particular modulation techniques. So, for FSK, very simplistically, if you are using binary FSK, you have one concentration of a main lobe here at omega 1 pertaining to frequency 1 and 1 at omega 0. The spacing omega 1 minus omega 0 is 2 delta omega. It is called the frequency shift. Frequency shift from an apparent carrier. So, if you pass your FSK spectrum through a non-intelligent detector and decoder and ask it to determine the carrier frequency, it might mistakenly give you this center point as the carrier frequency. So, this is called the apparent carrier frequency. So, when you have to specify any FSK modulator or demodulator, you specify in terms of the center frequency, the phase shift, and the frequency bandwidth of F1 and F2. Now, let us shift gears and move into something called as minimum shift keying. What is minimum shift keying? It is a special type of continuous phase FSK. So, we have entered the domain of continuous phase modulation techniques, and we will stay there. The modulation index for minimum shift keying is 0.5. How do you define a modulation index for the case of FSK? Well, it is given by K subscript FSK equal to 2 delta F over RB. Delta F is the frequency separation, RB is the bit rate. So, minimum shift keying has the property that the modulation index is 0.5. The other important characteristics of minimum shift keying are constant envelope, highly desirable, works well for relay fading environments, good spectral efficiency, we will find out how good is it in the subsequent slides, good bit error rate performance, it is scoring high on all of these things, spectral efficiency, bit error rate performance, continuous phase. No doubt MSK is one of the popular modulation techniques. It also has a self synchronizing capability. So, let us now go deeper into minimum shift keying. Just one more point, minimum shift keying is also called fast FSK. Why? Because the frequency spacing used is only half as much as that used in a conventional non-coherent FSK. We are talking about the frequency shift between F1 and F2, the two frequencies used to denote 1 and 0. Let us see how we can represent an MSK signal. So, let us say ST can be represented as S1 phi 1 t plus S2 phi 2 t, where t lies between 0 and the bit interval TB. Now, what are phi 1s and phi 2s? Phi 1 for MSK is given by under root 2 over TB cosine pi over 2 TB t times cosine 2 pi FCT, and it lasts from minus TB to TB. But please note, phi 2 is shifted in time. It is under root 2 over TB sine of pi over 2 TB t sine 2 pi FCT, but please note this time is from 0 to 2 TB. Please note there is a time shift between phi 1 and phi 2. In some sense, we can equate it to offset QPSK. In fact, in offset QPSK, we use rectangular pulses shifted by TB by 2. Here, instead of rectangular pulses, you are using the half cycle of cosine. Other than that, it is very similar to your offset QPSK. So, here is phi 1 and here is the phi 2 that will plug in and multiply to get your ST. Please note, these method of representation of an MSK signal will lead to how you build the modulator and then the demodulator. We will have a simple multiplication of cos 2 pi FCT with cos pi over TB t to begin with, to create the basis functions, right? And then you create this S of t, multiply it with message bits and send it out. Here is a simple representation in the time domain. The first figure shows the time domain input binary sequence. So, 1 1 0 1 0 0 0. Suppose this is an example we are taking. When you use the previous slide to find out phi 1 and phi 2 and multiply it, you get this kind of a waveform for S1 phi 1 t, and clearly a time shifted S2 phi 2 t. When you add it up, magically you reach a continuous wave FSK. Please note that the places where there is a 1, there is a higher frequency, and the moment you enter the domain of 0, correspondingly there is a lower frequency, and then again higher frequency and then lower frequencies. Right. So, this is how MSK works. It is spectrally one of the most efficient continuous phase modulation techniques. Now, let us use our understanding of the MSK signals and build a transmitter. We first start with cos 2 pi FCT and multiply with what? Cos pi t over TB. These were the two things we multiplied with. If you remember, phi 1 t is cos pi over TB t cos 2 pi FCT, and we multiply it. Here is what you get. And so, this is how we are trying to build our phi 1. Pass it through the binary, the band pass filter centered around F1, pass this one through the filter centered around F2. So, these are narrow band pass filters. Add it up and you get your phi 1 and phi 2. Now, all you have to do is multiply by M1 and M2 t and send out the MSK waveform. So, this is a simple transmitter for MFSK. Now, how does the MSK receiver look like? Is just the reverse. You again start with your phi 1 and phi 2 t, which you can generate locally. Take the input, split it up, multiply it, integrate it, pass it through the decision device, estimate the phase, logic circuit, and find out the binary output waveform. So, this is the MSK receiver. It is fairly easy to construct. Now, the other aspect is what is the power spectral density of an MSK. For MSK, the baseband pulse shaping function is given by Pt, which is nothing but cos pi t over 2 capital T, and it is 0 elsewhere. In this case, if you use this pulse shaping function, then you have the power spectral density of MSK given by the following equation. Please note, it is here f plus fc and here f minus fc, and the denominators are same. So, there is a symmetry around fc. How does it look like? Only on the positive side, here is your MSK, and to compare it with, we have the power spectral density in the background for the QPSK or also the offset QPSK, which has a similar power spectral density. So, couple of things that can be noted. Please note, this is the x axis representing frequency and y axis is in dB. The first thing that we observe is that the main lobe of your MSK is broader than QPSK or offset QPSK, which means it requires a little bit more bandwidth. But this comes at an advantage. The advantage is that the side lobes are greatly reduced. When I say greatly, please note that the y axis is in dB. So, here there is almost a 20 dB reduction with respect to the first side lobe of QPSK, which means most of the energy is present in the main lobe, and usually the bandwidth is measured with respect to the main lobe only. So, it is a good property. So, for your MSK, the power spectral density is fairly conducive. Now, what are the advantages of MSK over binary FSK? See, both MSK and binary FSK produce constant envelope carrier signals with absolutely no amplitude variations. This is a desirable characteristic for improving the power efficiency of the transmitters. You can use the class C amplifiers. The amplitude variations can exercise non-linearities in an amplifier's amplitude transfer function. What does it do? It generates spectral regrowth, a component of the adjacent channel power. Therefore, more efficient amplifiers, which tend to be less linear, can be used with constant envelope signals, reducing power consumption. Now, let us look at one variant of MSK called the Gaussian MSK. This is popular because it has been adopted by the GSM standard also. So, how does it differ from MSK? GMSK is a simple binary modulation scheme. Okay. The beauty is in its simplicity. It is a derivative of MSK, we will soon see. And how is it derived from MSK? The side lobe levels of the spectrum are further reduced. Which spectrum? The spectrum of the MSK are further reduced by passing the modulating non-return to zero data waveform through a Gaussian pulse shaping filter. So, you first pass the waveform, data waveform through a Gaussian pulse shaping filter and then use the MSK. It will clearly give you better spectral properties because you are doing pulse shaping. But we will see that the price is not too much. Gaussian baseband pulse shaping smooths the phase trajectory of the MSK signal. Now, let us see how a GMSK transmitter looks like. So, the implementation is fairly simple. You have a non-return to zero data 1 0 0 0 1 1 0 1 1 which is coming in. It is first passed through a Gaussian low pass filter which actually smooths the edges, and what you obtain is B of t. Now, in this case your M is equal to 0.5. So, you use an FM modulation. It is a fairly evolved technology, and then what you send out is Gaussian FSK. Please note the implementation is very simple and hence very inexpensive. You can also go the MSK route where the GMSK modulator uses the quadrature components to generate the quadrature GMSK. Again, you have the non-return to zero input E of t. First, you pass it through the Gaussian low pass filter. Now, the Gaussian low pass filter will also be characterized by a parameter called alpha, which decides how broad or narrow is the low pass filter, basically the roll-off factor. Okay. That is a design parameter. Once you pass it, you get Bt, you integrate it, split it, pass it through cos and sine filters, get xt's and yt's, multiplied by the local oscillator sum and send it. So, this is the simple implementation of quadrature Gaussian minimum shift key. Now, let us compare how does GMSK stand with respect to MSK. Now, here on the leftmost column is the product of time and bandwidth, the time bandwidth product given by BT. Here it denotes the different kinds of GMSK possible for the different roll-off factors alpha. This comes from the Gaussian filter. So, it is 0.2, 0.25, 0.5, right, and when it becomes very, very large, say infinity, it becomes MSK, right. So, here let us look at an example. How much power is contained within a certain bandwidth? So, if I want to take this example of MSK, what it means is that 99% of the power is contained within a bandwidth B equal to 1.2 divided by T, or BT is equal to 1.2. It means for MSK, 90% of the power is contained in a bandwidth equal to 0.78 divided by T, and so on. So, you can become as stringent as possible. At the same time, please compare it with some of the GMSK schemes. Consider, for example, 0.5 GMSK. If you use the same parameter, how much power of 0.5 GMSK is contained within 1.04 by T of the bandwidth? The answer is 99%. So, clearly a much smaller band contains the same amount of power. If you choose to move further up and you have a more sharper roll-off factor, so if you look at 0.2 GMSK, then hardly 0.8 over T is the bandwidth requirement for 0.2 GMSK to contain 99% of the power. So, it is a very spectrally efficient schemes. This table gives you how much strict you want to be on the x-axis and how lenient you want to be in terms of choosing your GMSK. So, in this slide you can also see that MSK is a special case of GMSK. Now, let us get a better feel of power spectral density of GMSK. Please note that other than having analytical expression, a lot of simulations are carried out to determine the power spectral density of GMSK, because actually it depends upon what kind of data that you get. It is data dependent. So, you average out over a lot of data sequences and then come up with some kind of a power spectral density depiction for GMSK. So, the curves are not that smooth. Please note that the topmost curve corresponds to MSK, MSK where BT is equal to infinity, and then you come down as you increase, the product decreases from infinity to, if you have 1, 0.7, 0.5 and so on and so forth up to 0.16 is depicted. This is the roll-off factor which we are talking about. So, as you decrease your alpha, you start packing in more power within the main lobe and you decrease the value of the side lobes. Please note that the y axis is in dB and the x axis is the normalized frequency given by f minus fc t. So, this diagram gives us some feel for the power spectral density. This also shows that your MSK is a special case of GMSK. Let us now consider how does a Gaussian minimum shift keying receiver look like. Let us say you have a modulated IF input signal coming in, you pass it through a splitter, then you multiply it with a sine and a cosine. So, pi by 2 shifted here, sine and cosine, this is a local oscillator. Please remember that the input signal has itself been taken through a clock recovery circuit and then generated the loop filtering, and which will tell you where the phase of the local oscillator should be. Now, once you multiply, you pass it through low pass filters, do some kind of a thresholding, add and get the demodulated signal. So, exactly how you construct it, you take it apart. What are the advantages of GMSK over MSK? Clearly, spectral efficiency is an advantage we have already seen. What are the other advantages? GMSK is a derivative of MSK, where the bandwidth required is further reduced. How? By passing the modulating waveform through a Gaussian filter. The Gaussian filter minimizes the instantaneous frequency variations over time. GMSK is a spectrally efficient modulation scheme and is particularly useful in mobile radio systems. It is a standard in GSM. It has a constant envelope, spectrally efficient, good BR performance and self-synchronizing. So, a lot of advantages of GMSK. Now, we shift gears and look at a combination of linear and constant envelope modulation techniques, basically a sneak preview on MPSK, and then in the subsequent lectures we will try to see how we deal with quadrature amplitude modulations, etc., and finally the spread spectrum techniques. So, let us say the Emery signal set can be expressed as S MPSK in time domain under root ES. This denotes the energy per symbol, cosine I minus 1 pi by 2 phi 1 t plus ES sine I minus 1 pi by 2 phi 2, where I goes from 1 to up to m because it is an Emery signal set. So, I have two phi 1s and phi 2s, and then we have this sinusoids here. Since there are only two basis signals, the constellation of Emery PSK is two-dimensional. The Emery message points are equally spaced on a circle of radius under root ES centered at the origin. So, if you increase the radius, you are actually pumping in more energy per symbol, and as you increase the radius, the separation between the points in the constellation diagram increases, giving you better signal to noise ratio. The probability of error, the average symbol error probability of a coherent Emery PSK system in additive white Gaussian noise or AWGN channel is given by the following equation. It is upper bounded by 2 Q function under root 2 EB log to the base 2 m over n naught sine pi over m. So, you can derive this equation. It is available in standard textbook. We are not going into the derivation, but it gives you a feel as how, as you increase the m, your probability of error increases. The symbol error probability of a differential Emery PSK system in additive white Gaussian noise channel is given by 2q under root 4 ES over n naught sine pi over 2m. What is the performance of symbol error probability for different values of m? Here, let us see, on the x axis we have plotted EB over n naught, on the y axis is the symbol error rate, and there are lot of curves. These are called the waterfall curves because of their way they look, and let us look at case 1, m is equal to 2. So, this is actually m is equal to 2 BPSK. As you can see, it up to 10 dB EB over n naught, it goes to fairly low values, 10 to the power minus 5, which is an acceptable performance region. The moment you go from 2 to 4 or 16, you have to have a higher EB over n naught to reach the same performance. So, now you are close to about 18 dB EB over n naught to reach the same performance level of 10 to the power minus 5. But clearly, since you have 16, m is equal to 16, you are sending 4 bits per symbol. If you are more greedy and go into 64, again for 64 you have to have an EB over n naught close to about 27 dB, so as to get the same performance of 10 to the power minus 5. So, there is a trade off between the bit rate and the probability of error. Now, let us spend some time looking at the power spectra of emery PSK. The power spectral density PSD of an emery PSK signal with rectangular pulses is given by this following equation. So, you have this sinc squared terms here centered around Fc, and if you write Es in terms of Eb log to the base 2m, then you get the following expression. The symbol duration Ts of an emery PSK signal is related to the bit duration Tb by Ts is equal to Tb log to the base 2m. In this slide, we have plotted the power spectral density for two cases, m is equal to 8 and m is equal to 16. Here again, with m is equal to 8 and raise cosine filter alpha is equal to 0.5 brings it down lower, and again m is equal to 16, raise cosine filter alpha is equal to 0.5, it brings it down lower. So, what can be learned from this slide is that the power spectral density looks as follows. This is in dB scale, therefore, the sinc functions look much more rounded, and the m is equal to 16 case is spread out, m is equal to 8 case is a little narrower in the spectral content. Please note they are both centered around Fc. Power efficiency and bandwidth efficiency of an MSK signal. So, let us look at the constellation diagram where you have m is equal to 2 scenario, m is equal to 4 QPSK, 8 PSK and 16 PSK. Now, if you have not increased the radius of the circle, which is under root EFS, then as you are packing in more and more number of symbols on the circumference of the circle, they tend to get closer and the probability of error will go up. But in this slide, we are talking about the bandwidth efficiency. Let us look at this table. Here on the first row, we have put down the numbers m is equal to 2, 4, 8, etc. for the MPSK. The second row denotes the eta b, which is the efficiency bandwidth given by RB over B star. What is B star? B star is the bandwidth measured between the first null bandwidth of emery PSK signals. So, clearly as you increase from m is equal to 2 to 4 and then to 8 and so forth, gradually your RB over B star increases. Okay. So, bandwidth requirement increases, but RB increases much faster. So, therefore, you can see a general increase. In the previous slide, if you see, the first nulls are different. So, the first null bandwidth is different from for m is equal to 8 and m is equal to 16. However, the RB also increases, leading it to a larger value of eta b. The third row plots for a particular bit error rate. Here we are taking 10 to the power minus 6, the EB over N naught requirement. As we saw in the waterfall slides earlier, for the same bit error rate, you need to increase the EB over N naught as you increase your M. So, here is a plot of how your requirement for EB over N naught increases. So, clearly there is a trade-off. If you are working in a low SNR scenario, then you have to resort to a smaller value of M, but the price you pay is poorer efficiency. If you are lucky enough to have very good SNRs between 25 to 30 dB, you can easily choose somewhere between M is equal to 32 and 64. So, couple of comments on power efficiency and bandwidth efficiency. Increasing M implies that the constellation is more densely packed as seen before, and hence the power efficiency or noise tolerance is decreased. This is intuitive. But the bandwidth efficiency perspective is different. The first null bandwidth of Emery PSK signals decrease as M increases, while RB is held constant. Therefore, as the value of M increases, the bandwidth efficiency also increases. Let us now summarize today's lecture. We took a look at constant envelope modulation techniques. Specifically, we talked about binary FSK or binary frequency shift keying. We then graduated to another technique called minimum shift keying, which is spectrally more efficient. A derivative of minimum shift keying called the Gaussian minimum shift keying was studied next. Finally, we took a look at Emery PSK and its power spectrum. We will conclude our lecture here, and in the subsequent lectures we will talk about quadrature amplitude modulation and also spread spectrum techniques. Thank you.